Hello people, welcome to my video. In this video, I am going to teach you the instruction DAA. DAA stands for decimal adjust after addition. Before starting the instruction, this instruction is extremely useful, not only as a student but also in the real life. Every processor, if you are studying 8086 or 8085, microcontroller 8051 or Intel Pentium, ARM, PIC, any processor, every processor has this instruction. Now, one instruction is common among all these processors. It must have some real world applications, right? Now, let's start. It is used by you, the programmer. You use it after performing an addition. We don't use after performing every addition. It is used after performing a decimal addition. Addition of two decimal numbers. Now get this clear. Every processor, any processor you study works with hexadecimal system, but the real world works with decimal system. Okay. For example, if you go to a mall in which you buy some products, at the end you make up a bill. The machine that makes up the bill, that adds the total sum of the products, has a microprocessor in it which works in hexadecimal system, but the product values you are entering, the numbers you are entering are in decimal system. Someone has to bridge this gap. We are entering decimal system and we are getting a result of decimal system, but the calculation and the background is happening in hexadecimal system. Now let's look how. To do DAA, you have to perform an addition. You did an addition and you got a result. Let's say the result is stored in AL register. If you are working with 8086 or any of the Intel processors, the result is stored in AL. If you are working with 8085, the result is stored in A register. Okay, you added two numbers and the result is stored in AL register. AL is an 8-bit register. It has a lower nibble and higher nibble. Suppose 53. 3 is the lower nibble and 5 is the higher nibble. Now, DAA works as follows. If the lower nibble is greater than 9 or auxiliary carry is equal to 1, then add 6. If higher nibble is greater than 9 or carry flag is equal to 1, then add 60. It's very simple. You should have a perfect example. Now, look at this. 30 and 20 are the product values. For us, they are decimal numbers. For microprocessor, it's hexadecimal number. When the cashier in the mall enters 30 and 20 and adds it, we get a result 50, obviously. For microprocessor, 30 is a hexadecimal number and 20 is a hexadecimal number. Now, let's see its addition. 0 plus 0, 3 plus 2, 5. We got the desired answer. Okay. Now for this example, 4 plus 4, 8, 2 plus 2, 4. Again we got an answer. 5 plus 4, 9, 2 plus 2, 4. Got this. We got an answer. Now the problem lies here. When you add 25 plus 25 in decimal system, we get a result 50. But for microprocessor, it gets 4A. Now, did you understand the problem? This is the problem and that's the solution, DAA. First you have to understand the problem before you start studying something. Let's see the solution for this problem. If your microprocessor adds up 25 plus 25, there is no way to get 50. It gets 4A. If it gets printed in the bill, it's just nothing because the real world doesn't know what is the decimal system. Then what we should do? We should adjust. We should adjust the result. That's where I section comes into the picture. Decimal adjust after addition. Now it looks like this. The result is stored in AL and if lower nibble is greater than 9, then add.
Why 9? Why 9 so special? Up to 9 in decimal and hexadecimal system they are quite same. But after 9 in hexadecimal system, the characters comes into picture. But our result should be character free. This is our requirement. Here in this example, the lower nibble is not greater than 9. Here 8 is not greater than 9 and same here. That means we don't need any adjustment here. But in this example, the lower nibble is a, which is greater than 9, and we need adjustment here, and it is the problem. And we have a solution too, which is DAA. Whenever lower nibble is greater than 9, we should add 6. Now, why 6? Our requirement is the lower nibble should be character free. To be character free, the 6 characters should be bypassed. After bypassing these 6 characters, we again get a decimal number, which is our requirement. So we are adding 6. Now let's do here. Let's do it together. Now for lower nibble, let's add 6. 4a plus 1, 4b, 4b plus 1, 4c plus 1, 4d plus 1, 4e plus 1, 4f plus 1, 5, 0. Now this is how the processor does an addition. Let's do some more examples. 26 plus 26 in hexadecimal, because processor is doing addition. 6 plus 6, 12, but in hexadecimal system it is C. 2 plus 2, 4. Now as the lower nibble is greater than 9, we should add 6, because our requirement is character free. Now let's do it together. 4c plus 1, 4d plus 1, 4e plus 1, 4f plus 1, 5, 0 plus 1, 5, 1 plus 1, 5, 2. Now 26 plus 26 is equal to 5, 2. Let's do another example. 28 plus 28 in hexadecimal system, because it is done by processor. 8 plus 8, add 8 to 8. 8 plus 1, 9 plus 1, 10. No, yeah, because it is hexadecimal system. Plus 1 B, plus 1 C, plus 1 D, plus 1 E, plus 1 F, plus 1, 1, 0. I added 8 to 8. After 9 in decimal system, I should get 10. Now 1, 0. The 1 is called as auxiliary carry. We have two conditions here. If lower nibble is greater than 9, add 6, or auxiliary carry is equal to 1, then also add 6. Now 2 plus 2 plus 1, 5. Add 6 to lower nibble. Now 50 plus 6, 56. Now let's see another example. 50 plus 50. Now here 5 plus 5, yeah. Here, if higher nibble is greater than 9, add 60. Now we are not actually adding 60, we are adding 6 to the higher nibble. If you are adding 6 to the higher nibble, obviously the lower nibble is been added with 0. So we are saying it as 60. Now add 6 to the lower nibble. Let's do it together. A plus 1 B plus 1 C plus 1 D E F 1 0. Now the lower nibble is just quite same, 100. 50 plus 50 is equal to 100. Now we have seen this case, and this case. Let's see this one. $80 plus 80. Here 8 plus 8. We have added 8 plus 8 in the previous example, and we got a result of 10 in hexadecimal system. Let's use it. Let's not waste time. Here the lower nibble is not greater than 9, but the carry flag is 1. Whenever the carry flag is equal to 1, add 6 to the higher nibble. Now which is higher nibble here? This is higher nibble. Now add 6 to the higher nibble. 160. Here the desired output. Okay, now let's see another example. 99 plus 99. These are the decimal numbers we enter in the billing machine, but the microprocessor calculates in hexadecimal form. So we are keeping hex h here. Now add 9 to 9. 9 plus 1 A plus 1 B plus 1 C plus 1 D plus 1 E plus 1 F and plus 1 0 1 1 1 2. So 9 plus 1. This is carry 1 2. Now 9 plus 1 1 2 plus 1 1 3 1 3 here. Now let's check here. The lower nibble is not greater than 9. No need of adjustment here. Here the auxiliary carry flag is equal to 1. Now add 6 to the lower nibble. 1 3 8. Next, the higher nibble is not greater than 9. Then no need of adjustment. Up next, here the carry flag is 1. Now add 6 to the higher nibble. That means 6 to the higher nibble, 0 to the lower nibble. 6 7 8. Now 99 plus 99 is equal to 198. Look here. First, the lower nibble is not greater than 9. Next, the auxiliary flag is equal to 1. Then add 6 to the lower nibble. So we add 6 here. Now the higher nibble is greater than 9. Here the higher nibble is not greater than 9. And if carry flag is equal to 1, add 60. Here the carry flag is equal to 1, add 6 to the higher nibble, and we got the desired result. Hope you enjoyed learning.